Hello. Today's lesson we will discuss the concept of electric field. What is a field? The concept of field can be used to explain any force. Now, what are the type of forces that you are familiar with? Force between two objects, whether it is electrical, magnetic, or gravitational, can be explained using the concept of a force field. A field is a three-dimensional space where a force can be detected. What does that mean? A field is simply a space where a force can be detected. For example, the space around the Earth where the gravitational pull of the Earth is felt is called the gravitational field of the Earth. Now tell me, why does this basketball fall when I drop it? What's the reason for it? It falls because the basketball is placed in the gravitational field of the Earth. Now you have seen this. The gravitational force between Earth and an object of mass m is Fg, the gravitational force, equal to g mass of the Earth times mass of the object over the square of the distance between them, and we call that the weight of the object. So weight, an object has weight because it is placed in the gravitational field of the Earth. If you take an object away from the gravitational field, it will cease to have any weight. An object of mass m has a weight mg because of the pull of gravity on it. In the same way, there is a space around an electric charge where it exerts force on other charges. If this is an electric charge, there is a three-dimensional space around it where this charge will exert force on other charges. And this space is called the electric field of that charge. Well, a positive charge attracts a negative charge. Why? Because the negative charge is placed in the electric field of the positive charge. In the same way, a positive charge repels a positive charge because this positive charge is in the electric field of the first positive charge. The force between two electric charges arises because each charge is placed in the electric field of the other charge. Here I have a positively charged object. The positively charged object has an electric field around it. Now, what happens if I place a negatively charged object in the space surrounding it? This is going to experience a force. What kind of force? An attractive force. What is the reason? The negative charge is placed in the field of the positive charge. Well, let me see if I can illustrate that using a simple animation. Now, this animation shows a negative charge at the center here. I don't know whether you can actually see it. It is colored yellow. That's a negative charge. And very small positive charges are distributed in the three-dimensional space around it. Now, what is happening to all those negative charges? They're all falling towards. You see that? Now, that is, well, you can explain it any way you want. If this is a positive charge at the middle, then all these negative charges are falling towards it. Just like objects placed in the gravitational field are falling towards the Earth, the electric charges placed in an electric field will move. If this is a positive charge, then the negative charges will all move towards it. If this is a negative charge, then positive charges will all move towards it. That's a beautiful illustration of how a three-dimensional space around a charge exists where the electric charge exerts force on other charges. Alright, let's take it away and continue with our discussion. So I hope you have a concept of what an electric field now is. Electric field is a three-dimensional space around an electric charge where it exerts force on other charges. Now let's talk about the intensity of electric field. How intense is the electric field caused by an electric charge? Now, electric field is a vector quantity. I hope you understand the meaning of a vector quantity. It has a magnitude and a direction. A force always exists in a given direction. So, an electric field is actually a force. And therefore, it has a magnitude and a direction. Electric field is a vector quantity. The magnitude of the electric field at a point is called the intensity of the electric field. Intensity of the electric field is a measure of the force experienced. Is that right? It's the magnitude of the electric field or the strength of the electric field. Now, we represent the electric field by the capital letter E. Whenever we want to represent an electric field, we use the capital letter E. And I have the definition of electric field. The intensity of electric field at a point is defined as the force experienced per unit test charge placed at that point. What does that mean? If I want to find the electric field caused by this electric charge at this point where I'm pointing, what all I need to do is place a unit test charge. What kind of a unit test charge? A positive test charge. Per unit positive, place a positive test charge at that point. Measure the force on that positive test charge. And that will be a measure of the electric field intensity or the strength of the electric field. Now, electric field at a point is a vector quantity, therefore it has both magnitude and direction. Now, let's say Q0 is a test charge placed at a point P, a distance r from a charge Q. Alright, this is a charge Q, say positive charge, and I have a point P where I'm going to place a test charge Q0. A test charge is a very small charge, and very often we call it a unit charge. Well, Q0 is a test charge. Now, what is the force experienced by this test charge because of the charge on this object? Can you tell me what that force is going to be? The distance between the test charge and the charge Q is r. So, using Coulomb's law, we can now write an expression for the force experienced by this Q0. What is the force experienced? F equal to K Q Q0 over R squared. This is the charge on this charge. Q0 is the test charge. And so, the force F experienced by the test charge due to the charge Q is K Q Q0 over R squared. Well, the force experienced by unit test charge. Now, suppose the value of this test charge is 1 unit test charge. If it is 1 coulomb, what is the force per unit charge? How do you find that? If this is a measure of the force on a charge of Q0, what is the amount of force on 1 coulomb? Force per unit charge. What all I need to do is divide this force by Q0. So that will be F over Q0 and that will be kq over r squared. So F divided by Q0 is kq over r squared. And what does this quantity give you? It gives me the force per unit charge. And that is the definition of the electric field. The electric field at a point due to a charge Q is the force per unit charge when the unit charge is placed at that point. And the measure of that force per unit charge is kq over r squared. So this is a measure of the electric field E at the point P due to the charge Q. Alright, note all those details. This is a measure of the electric field at the point P due to this charge Q. Okay, and so watch that. The electric field at a point, distance r from a charge Q, is E equal to kq over r squared. Now, this is the magnitude of that electric field. The direction of the electric field we will discuss as we go on. And now, what is the unit in which the electric field is measured? Look at this, the definition of electric field. Electric field is force per unit charge. So it is measured in Newton per Coulomb. Force is measured in Newton. Charge is measured in Coulomb. Force per unit charge is Newton per Coulomb. Alright, if a charge Q coulombs is placed in an electric field E Newton per Coulomb, what will be the force on that charge? Can you tell me? Now, I have an electric field, and in that electric field, I'm going to place a charge Q. That means that charge is going to experience a force because it is placed in an electric field. Just like the basketball is placed in the gravitational field, it experiences a force. What will be the force this charge experiences? Well, in order to give me the answer, you must know the meaning of electric field. Electric field is force per unit charge. If E is the force per unit charge, then what is the force on a charge Q? It will be E times Q. I hope you understand that. By definition, E is the force on 1 coulomb of charge. Electric field is the force on 1 coulomb of charge. Therefore, what is the force on Q coulomb of charge? What is it? F equal to Q times E. A very important relation you cannot afford to forget. The force experienced by a charge Q placed in an electric field E is F equal to Q times E. Now, because the charge Q now is under a force, this charge will experience an acceleration, isn't it? Whenever there is a net force on an object, that net force will create an acceleration on the object. So this force will produce an acceleration on that object. The value of that acceleration will depend on the mass of the object that is charged. Well, let me see if I can show you what actually this means. When an object is placed or when a charge is placed in an electric field, it will experience a force and therefore it will accelerate. Give me a second. Now here I have a beautiful illustration of this is an electric charge, and look at a charge placed in the field, how it behaves. As it comes closer and closer, the acceleration increases, speed increases. And just like a comet comes and orbits around the sun and goes away, there you have the electric charge. Well, I got that charge behaving like this because I picked a charge here and sent it in that direction. And you can see the force on it. Look at the arrow. The force on it becomes larger and larger as it comes closer to the charge. Okay, now look at, if I place a charge here, look at the way it's going to move. Watch that again. Alright, I'm going to place one charge there. Look at the way that's going to move. If I place one here, you should notice when I place a charge here, the force on it will not be that great. So it will move slowly, but as it comes closer and closer, the force increases, the acceleration increases. And so the acceleration, the object, the charge will experience a greater and greater acceleration, just like the orbiting charge here. Now, look at a couple more examples. If I place a charge here, it goes that way. If I place the charge there, you can see anywhere I place a charge, it moves towards it. That means the space around that red charge describes an electric field. So this is a beautiful illustration of what an electric field actually does. Alright, let's now talk about the direction of an electric field. What is the direction of an electric field? Now, the direction of an electric field is defined as the direction in which a positive test charge would move. So, don't forget that. Our test charge, our standard test charge is a positive test charge. Now, you might ask me, why didn't you take the negative test charge as the standard? Well, we've got to choose one, and that is, happen to be the positive. So, the direction of an electric field is the direction in which a positive charge would move. A positive test charge would move. Now, here I have constructed an electric field. We will soon see what these lines actually mean. Now, this is a positive charge, this is a negative charge. If I place a positive test charge, remember our test charge is positive. The standard test charge is positive. If I place a positive test charge here, what will be the path that test charge is going to take? You will notice that because this is positive, it will move away from the positive and towards the negative. That means it will take a curved path. Is that right? Now watch, I'm going to make it move. And watch how it's going to move. Is it going to move? Yes, it is moving. You can see it is moving because under the influence of the two forces, because the positive charge repels it and the negative charge attracts it, so it moved along that curved path. Now all these lines in here are actually the paths that a standard positive charge will take when placed in this field. If I place the unit positive charge here, it will move away like that. It will move away from the positive charge and ultimately towards the negative charge. If I place the unit positive charge here, it will move like this. You see? That's a beautiful way to construct an electric field, to visualize an electric field. Okay, let's move on. Now, since a positive charge will move away from a positive charge, the field due to a positive charge is always directed away from it. Is that right? Yes, because our standard test charge is a positive charge. And a positive test charge will always move away from a positive charge. That means the electric field due to a positive charge will be always directed away from it. And Similarly, the field due to a negative charge is directed towards it. A standard positive test charge will move away from a positive charge and towards a negative charge. Now here I have constructed the electric field due to a negative charge. Look at the arrows. These arrows are all pointing towards the negative charge. That means the standard positive charge placed anywhere will move towards that charge. Now the paths taken by the test charge are indicated by these arrows. And I will tell you shortly that these lines with the arrows are actually called field lines. Lines that describe the field. What is actually a field line? A field line is the path that will be followed by the standard test charge, which is a positive charge. And look at the electric field due to a positive charge. If you place our test charge anywhere in the space around it, that test charge will move away. So the field lines are diverging from a positive charge, and the field lines are converging onto a negative charge. Well, I have now the discussion on electric field lines. You know what an electric field line is now. What is an electric field line? Well, an electric field line is the path followed by a unit positive test charge. The intensity and direction of an electric field can be better understood by drawing lines of force called field lines. Actually, once a number of field lines are drawn, it will give you a clear indication of the intensity of the electric field and the direction of the electric field. Now, I have defined a field line for you. What is a field line? A line of force. When I say a line of force, that is a field line. A line of force is the path taken by a positive test charge placed in the field. A very simple definition. Since a positive charge always moves away from a positive charge and towards a negative charge, field lines or lines of force are always directed away from a positive charge and towards a negative charge. And I have some properties of the field lines. Let's look at some of those. Property number one, field lines always originate at a positive charge and terminate at a negative charge. We talked about that already. The density of the field lines, that is the number of lines per unit area, is proportional to the strength of the electric field E. Now, what does that mean? But let me see if I can illustrate that to you. What that means is, if the field lines are all crowded together, now look at this. Field lines are, now I'm drawing some field lines. A field line should always be indicated by the arrow. Now, if you look at this, now I drew two rectangles. Well, I should have drawn both rectangles of the same area. Now, look at this rectangle. There are 3 plus 2, 5 field lines in there. And look, if you move that rectangle out, you can see that rectangle contains only 3 field lines. That means the intensity or strength of the electric field is much more here than here. So how closely are the field lines spaced? Give you an indication of the strength of the electric field or the intensity of the electric field. Okay. Now, here I have indicated that with this diagram. Here I have let me go back and give you that diagram one more time. Here I have a charged object. Can you tell me what kind of charge has this object got? Is it positively charged or negatively charged? How do you know? Well, the field lines are all originating from it. That means this is a positive charge. Now, if you look at the dark ring I have drawn there, if you notice that the field lines are very close in there. And if you go out, now look at that ring. The field lines are not as close there as they are here. So, around this circle, the field lines are closer together, and in this region, the field lines are farther apart. That means the intensity or the strength of the electric field is much stronger around here than around here. Why? Because as we move away from the electric charge, the strength of the field becomes less and less. Just like if you go away from the earth, the gravitational pull on you will become less and less and less. Okay, so property number 2, the density of the field lines, in other words, how close they are, or the number of lines per unit area, is proportional to the strength of the electric field E. Property number 3, the number of lines originating from a charge or terminating at a charge is proportional to the magnitude of the electric charge. In other words, the lines will be crowded around a large charge and less crowded around a small charge. Well, I will illustrate that in a minute. Property number 4, field lines always repel each other and they never cross. That's understandable because a field line is the path taken by a positive test charge. If two positive test charges are moving, can they ever come closer together? No, they will always be repelling. And that's therefore the property of the field lines. Now, property number 5. The strength of the electric field in a region is uniform if the field lines are parallel. Well, that makes sense. Where the lines are crowded, if the field is greater than where the lines are farther apart. Well, what happens if the lines are equally spaced all over? It means the field strength is uniform. So parallel field lines indicate that the field strength is uniform. Now let me go back to this. That's an important concept. We said the number of lines originating from a charge or terminating from a charge is proportional to the magnitude of the charge. What that means is, suppose I have here a very large charge, a large quantity of charge. There will be large number of lines of force originating from it. On the other hand, if I have here a very small charge, there will be only few lines originating from it. So the number of lines of force either originating from a charge or terminating, if it is negative, is an indication of the amount of charge. This is a greater amount of charge and this is a smaller amount of charge. Okay. Now, here I have an illustration. Density of lines in pattern. A, B, and C. Now, which of these carry a greater amount of charge? That will be easily understandable now, is that right? Which of these carry a greater amount of charge? A, B, or C? The number of lines of force originating from C are so much more than the number of lines of force originating from A or B. You may not be able to see the complete picture of C, but it gives you, whatever you can see, gives you a picture of the strength. C is a much bigger charge than A or B. Okay, let's now talk about another concept, electric flux. Now, what is the meaning of flux? Now, can you imagine I'm standing in a room where I have a wall on the right and a wall on the left. Suppose there is an electric field crossing this room, lines of force. Suppose you have a uniform, what does that mean, uniform electric field? All lines of force are parallel. Now, if I keep a certain area, now what is an area? I can find an area, well, let me look for an area that I can. Now here I have a flat, you see this one here? If I keep it at right angles to the lines of force, the lines of force are coming like this. That means all the lines of force coming are crossing this area. Now, the electric flux is a measure of the total number of lines of force crossing at right angles to any given area. The total number of lines of force crossing at right angles to any given area is called the flux crossing that area. So if you place an area across any field, there will be a flux crossing that area. The flux crossing that area is a measure of what? The number of field lines crossing that area at right angles. Okay, I have some illustrations here for you. So, the intensity of an electric field can be defined using the concept of field lines. The intensity of electric field E at a point in an electric field is defined as the number of lines of force crossing at right angles to a unit area containing that point. Now this time, when you want to define the electric field using the concept of flux, suppose now I am pointing in space. Suppose the end here where I'm pointing, I want to find the electric field at that point. So what do? I place a unit area, that means an area of 1 square meter. I place a unit area so that the point where I want to find the electric field is in that unit area. And now what do? I measure the electric flux crossing that unit area, and that is a measure of the electric field at that point. In other words, electric field is a measure of electric flux per unit area. That's what this means. The intensity of electric field E at a point is defined as the number of lines of force crossing at right angles. That is the electric flux. So I can replace this whole line, the number of lines of force crossing at right angles to that, and that can be replaced by the word flux. So it's a measure of the flux crossing a unit area containing that point. So one more time, try and understand this well. If I want to find the electric field at this point, what do? I keep a unit area there. I'm going to bring the unit area. I'm going to keep a unit area so that that point is on the area. Then I measure the electric flux crossing that unit area. That means electric field at a point is a measure of electric flux per unit area. And that flux must be at right angles to the area. It's very important. Alright. Now here I have an area. Can you see that area placed? Now if I want to find the electric field at this point, what all I need to do is place that unit area there and measure the flux crossing that unit area. Electric field E is a measure of the flux per unit area. I have another illustration here. You can see this is a circular area, and you see how the flux is crossing that area. To find the electric field at a point there, I construct a unit area there and measure the flux crossing that unit area. So once again, tell me, what is electric field in terms of electric flux? Electric field, or intensity of electric field E at a point, is a measure of the flux crossing per unit area that contains the point. The number of lines of force crossing at right angles to any given area is called flux on that area, and we will represent electric flux by the Greek letter phi. That's a standard representation. So electric field E is then the flux per unit area. That's what I've been talking to you so far. Electric field, or the intensity of the electric field, is the flux per unit area. How do I write it? E equal to phi divided by A. Is that right? Phi is the total flux on a given area. And that total flux divided by the area is a measure of the flux per unit area. So electric field at a point is a measure of flux per unit area. And therefore, if I want to calculate the total flux crossing an entire area, what do? Multiply the electric field. Electric field is the flux per unit area. Multiply that with the area. So E times A is a measure of the total flux. And what is the unit of the total flux? Newton meter squared per coulomb is the unit of electric flux. Alright. Now here I have an illustration of electric field lines crossing a given area. And I want to find the electric field at that point A. What is the definition of electric field at that point A? It is a measure of electric flux per unit area crossing at right angles. It's very important. Now, what you see here on the right is the cross-sectional view. In other words, that is the unit area placed here. So if you look at from behind, this is what you see, the flux crossing that area. Now I'm going to change the angle of that unit area and see what happens to the number of lines of force crossing that unit area. I want you to watch this. Now, as the area becomes tilted, you can see, as the area gets more and more tilted, you see the number of lines of force crossing that area will also become less. So, it is important to understand the electric field at that point A as the flux, the normal flux. What is the meaning of the normal flux? The lines of force must be falling at that area at right angles. If they are not at right angles, you need to take the component of the electric field at right angles. Alright? You don't need to worry about that, but at the moment you only understand that in order to measure the electric field at that point, the electric field lines must fall at right angles. Otherwise, you will not get the accurate value. So as the angle increases, you see the flux crossing the area will become less and less. And now, ultimately, when that area is parallel like this, there are no field lines cutting the area. And now, if I keep increasing the angle, the number of lines cutting will also increase. And finally, the number becomes maximum when the area is at right angles to the field lines. Okay. Let me take that away. Let's now look at electric field due to systems of charges. Now, you have seen how the electric field due to a positive charge will look. All field lines are originating from it. How does the electric field due to a negative charge look? Field lines are all converging to it. Alright? If you now have a system of electric charges, how does the electric field look? If a region contains more than one point charge, then the field at any point is the vector sum of the fields due to each charge. Remember, electric field is a vector quantity. Now consider two positive point charges as follows. There you got a positive point charge A and another positive point charge A. If you now look at each point, now the point where I'm indicating now, there is an electric field due to A, that is the blue vector, and there is an electric field due to B, which is the green vector. Why is the blue vector bigger than the green vector? Because the field due to B will be a small vector, because the point is very far from B. And the field due to A here will be much greater. And so, the net field here will be the vector sum of that. In the same way, if you look at this point, the field due to A, look at this, it is directed away from A. And the field due to B, if I have to draw a line away from B, look at that. That is the field due to B. So the net field here will be the vector sum of these two vectors. Well, you know how to find the resultant of these vectors. Alright. Now, there are two field vectors at every point. The field at each point is the resultant of these two. So, what is the resultant of these two vectors? Look at that. That red vector is the resultant of these two. That means the resultant electric field due to both A and B will be that vector. Similarly, the resultant electric field due to both A and B here will be that vector. And in here, look at this, the green vector due to B and the blue vector due to A, and the resultant vector will be somewhere in that direction. And in here, the blue and the green will add up the resultant vector. Alright. The net field due to two positive charges, therefore, will look like this. I have now drawn a number of field lines. What these field lines indicate is if I place a unit positive charge, what is the path it will take? If I place a positive charge here, it will go like this. In other words, it will be moving depending on the force due to both on them using the resultant direction. So the electric field due to two positive charges will look like this. You must be familiar with drawing electric field due to systems of charges like this. Field lines are originating from both, and you can see as a positive charge moves away from A and also away from B. Go like that. Now take a look, the detailed look at that, and make sure you understand the pattern of the electric field. Okay, so there is a point between the two charges. Look at this. There is a point between the electric charges there. There is no electric field. Why? Because the field due to the one on the left will be exactly equal and opposite as the one due to the one on the right. So there will be no electric field at the center. How about the field lines due to two negative charges? Can you construct the field lines due to two negative charges? Will it be different from the one we saw for the two positive charges? Well, these are the two negative charges. The lines, the orientation looks almost the same, but the field lines are now converging on these negative charges. And here again, you can see there is a point in between where there is no electric field. So the resultant field due to the two is similar to the field due to two positive charges. The only difference is that the direction of the field lines are in the reverse direction. Field lines due to two opposite charges. What will the field lines look if I have a positive charge and a negative charge? Can you construct one on your own? In other words, if you have a positive charge and a negative charge placed in space, what will be the path taken by the positive test charge placed at various points in space? Can you construct some field lines? Well, think about it. There you have one. This is a positive charge, this is a negative charge. That means if a test charge is placed here, it will move away from the positive and towards the negative. In fact, the animation I showed you some time ago, the moving of the test charge was exactly like this. This is the field lines due to a system of positive and negative charges. Well, you must be again familiar with it. You can see, if you look at areas here, there are some regions where the electric field lines are almost parallel. What does that mean? It means the electric field is almost uniform. All right. The field lines originate on the positive charge and terminate on the negative charge. In the region between the two charges, the field due to both charges are in the same direction. Did you notice that? Now, in the case of a positive and a positive, the point in between, there was no electric field because the field due to one was equal and opposite as that of the field due to the other. Whereas, when you have a positive and a negative, the field at a point in between are in the same direction. That means the strength of the field will be much greater in between. You can see the field lines are crowded there. If you go away, the field lines are very much separated. The strength of the field is weak in regions where the field lines are widely separated. The intensity of the field is high in this region. Which region? In the region between the two charges. The intensity of the field is high, as is indicated by the closeness of the field lines. Now, notice the parallel lines of force in between the two charges. We talked about that. Now, I have given 4 diagrams here of different patterns. Now, can you have a look at it and talk about it? Why do these electric field line patterns look the way they do? Alright, talk about this. This is the field pattern due to 2 positive charges. Now, what is the difference between the 2 positive charges? Can you tell me what at all, if there is any difference? What is the difference between these 2 positive charges? You can see there are only very few field lines originating from the one on the left. There are a lot of field lines originating from the one on the right. That means this is a much bigger charge than this. Similarly, what does this tell you? This tells me that the negative charge on the right is a much bigger charge. It contains a larger quantity of charge. Now here I have a positive charge and a negative charge. Now, which of these contains large quantity of charge? Well, of course, the negative, because large number of lines of force are converging onto it. Similarly, I have a positive charge and a negative charge. Now, you need to practice drawing some of these lines of forces representing electric field intensity. Alright, let's move on. Several field line patterns are shown in the diagrams below. Which of these patterns is incorrect? Explain what is wrong with each incorrect diagram. Now, I'm not going to talk about it. I'm going to show them to you. I want you to look at each of them and then tell me if the field lines are drawn correctly. If they are not, you've got to say why it is wrong. And you've got to make it out into a Word document and email it to me. Alright? I will be looking for that. And there you got 1, 2, 3, 4, 5. Or A, B, C, D, E. So write down A in your piece of paper and say whether the diagram is correct or wrong. If it is wrong, you've got to tell me why it is wrong. So look at each of these and decide what you will do. Alright? Well, I'm going to take it away now. You can print this out from the printable PowerPoint. And so use that to answer the questions and email them to me. Another one. John drew the following electric field lines for a configuration of two charges. What did he do wrong? Explain. Now explain to John what he did wrong. That is the diagram John drew. Alright? Write a couple of sentences about what he did wrong. Now all these, I'm going to give you some more exercises. I want you to answer all these and email them to me. Consider the electric field line shown in the diagram below. From the diagram, it is apparent that object A is dash and object B is dash. In other words, you need to figure out what is the charge carried by A and what is the charge carried by B, and complete this line and also include along with your work. Consider the electric field lines drawn below for a configuration of two electric charges. I have the electric field drawn for the configuration of two electric charges. Several locations are labeled on the diagram. Look at the locations: A, B, C, D, and E. Your job is rank these locations in the order of the electric field strength, from the smallest to the largest. In other words, where is the field strength weakest? Where is the weakest field? And where is the strongest field? You are required to put this point according to the strength of the field. Alright, include this also in your homework. Okay. Use your understanding of electric field lines to identify the charges on the objects in the following. Well, another exercise for you. Look at the field lines and decide which object carries what type of charge. A, B, C, D, E, F, G, H, I. Alright, tell me what type of charge is carried by all these. So include all these. It doesn't take a long time for you to do it. Just about a half a page all together. Observe the electric field lines below for various configurations, and isn't that what we just did? Rank the objects from greatest magnitude of electric charge beginning with the smallest. No, this is not. This is different from the earlier one. Now this time you need to look at the electric field configuration and then decide which of these A, B, C, D, E, F, G, H, I, J, which of these has the largest magnitude electric charge and which has the least magnitude electric charge. You know how to do that, is that right? Because the magnitude of electric charge is proportional to the number of lines of force either converging onto the charge or diverging from the charge. So use that concept to do this and put all these answers together and send it to me. Alright? Now, I'm not going to go into solving problems now. I'm going to do a second part of this lesson and I'm going to solve problems for you. Alright? So I'm going to stop this lesson here. I will see you for solving problems a little later today.